Okay, so if we have to aim at something, we are basically taking a measurement. And maybe you want to aim right on point. Very valid. Boom, you hit the middle. But what if your aim is really off? That's not very accurate at all. And not only that, you have another problem with scatter, where now, if you try to hit some value, and in experiment there are lots of random errors, so maybe you're gonna have all kinds of spray and you don't really exactly hit the middle because of all kinds of random recoil things and variables that you cannot really control. Sometimes it's a little bit more systematic and you see like, oh, I'm not hitting the target, but I'm constantly going off at a certain value. So that's the same thing when you're doing experiments, you're trying to hit values. The real value is right on point, but sometimes when we try to measure things, we don't really quite hit it due to random error, or we have some kind of systematic error. How do we describe these patterns in physics? That is what we're going to look at next.
So in physics, whenever you take a measurement, it's a little bit like making a hit shot. Okay, so if it hits your target directly, then your measurement is perfect. But if you've watched the previous video, you know that there's no such thing as a perfect measurement. Okay, so these are just trials to measure the exact value of a physical quantity. For example, if you want to measure your mass, there's no one perfect 100% accurate way to measure your mass. Such method does not exist, okay? Because we don't know for sure. Everything is just an estimate, okay? So right now, during your headshot, some issues may happen. For example, you may shoot and then you get some random scatter, okay? So let's say the middle of the cross eye is here. Looks like here. Let me zoom in a bit for you. Okay, let's say the middle of the cross eye is here. And I look at the bullet scatter. Oh, one here lah. There is one here lah. Oh no, I need to change thickness. There's one here, there's one here, there's one here, here. I mean, I'm pretty sure the person is not alive, if let's say this is a real person. But you can see the scatter is very random, all over the place. Okay, you got one scatter up, scatter down. So in this case, whenever there's a random scatter, in all direction, this is a particular pattern. So what do you think could happen to the gun that cause it to like shoot in random direction? It could be because teacher, the player hand not steady, he not steady from PP, he didn't hold the gun properly. Sure. Maybe the gun is not designed properly. Could be. Okay, so we're going to troubleshoot in this video. All right. The second kind of error or pattern that you will see is something like this. There's a systematic drift up. For example, when you shoot your gun, for some reason the gun go upwards. Okay, and because no measurement is exact and no measurement is perfect, this kind of systematic drifting up, you see the bullet hole, don't know why all drift up in one direction. There's a certain systematic trend. This is another type of error. So to help us differentiate them, I'm going to now define what are the two different types of error that is possible that you may encounter when you are doing readings. So let's say we look back at the same readings that you have done, okay, in the previous example. And I mean, I'm looking at these 5 numbers. I'm wondering, is it accurate? Don't know. And if there's an error, what causes the error? Well, in order to answer that, I actually need to know what is the exact diameter of my marble, right? Like maybe I check the box, the packaging, I go and check something, figure out what the diameter is. Call the manufacturer. Okay. So if let's say I call the manufacturer and I say, hello boss, what is the diameter, this diameter of this marble that I buy from you? Okay. And then the boss say, well, the true reading or the true value is 2.8 cm. And I go like, nani? You look at all this reading, why all so small? Every reading here is less than 2.8. Oh no! So, assuming that the marble that you got is the perfect marble and the manufacturer didn't lie to you, that means your measuring got problem, got error. And it's a systematic error. Teacher, what means systematic? Systematic is when the value that you measure, this 2.5, 2.49, 2.48, 2.51, all this, is consistently smaller than the true value. Can be consistently bigger. Can. Okay? So let's say, for example, you're supposed to get 2.8, but all your numbers are less than 2.8. Systematic error. You're supposed to get 2.8, but all your numbers are bigger than 2.8. Systematic error. Okay? So if you think about this, let's say you draw a number line instead of a two-dimensional bullseye. This is 2.8 cm. Okay? Or 2.80 cm. If whenever you take a reading, all your reading is here, systematic. If whenever you take a reading, all your reading is here, systematic. Okay? So it's always smaller than or greater than the true value in one direction. So the measured value is always either larger than or smaller than the true value. Always. So it's always either smaller than, for example, if you look at these plots, or always greater than. Okay, so what are the source of your systematic error? What could cause this systematic to happen? Whose fault is it? Well, if let's say you use a ruler, there could be that when it's supposed to be 0, it didn't give you 0. And we call that zero error. Okay, so could be 0 error. The main SASA is your instrument. Maybe the micrometer screw gauge is too tight. Maybe the vernier caliper rail is a bit off center. Okay, so 0 error is due to the instrument. So maybe, so when you want to define 0 error, you will say that the instrument has reading even when nothing is measured. It's like that wonky weighing machine you have at home that could be as old as you, and you already know one. The needle is off a bit. Okay, so 0 error. Okay, of course, the other problem, number 2, could be incorrect calibration. What is calibration? Okay, you're going to see some examples of that in the video, in the upcoming videos. But incorrect calibration simply means the scale that is on your ruler or on your meter. Okay, the only ruler I have in my table now is this protractor because I was recording another video. Okay, maybe they print wrongly leh. You see all the this one here. Maybe they print wrongly. Don't know. So it could be incorrect calibration. Incorrect calibration of the instrument. In other words, whenever there's systematic error, sus the instrument. Maybe the instrument got problem. Maybe the technique got problem. Okay, maybe you didn't use it correctly. It's the instrument part. Okay, so how can we improve? Take average. Miss, I know. Always improve experiment. We take average. I'm going to stop you there. If the instrument is broken or faulty, and your reading is always smaller than, you average the reading that is always smaller than, you will still get a reading that is smaller than. So it's not going to help, right? So I'm going to put a big note here or a big red star here and say, unfortunately, systematic error cannot be improved by taking repeated readings. So the improvement cannot be done by taking repeated readings and average. I will tell you what taking repeated reading and average help. It only helps with precision. The precision of reading. Teacher, what is precision? Well, that's in the next video. But in short, precision means what is the smallest decimal point that you can read. Only helps with precision of reading. So then how can we improve leh? We can improve this by taking the zero error and then subtracting the reading. Okay, so improvement number 1, the actual reading or the real value, I would say true value. We will take the reading minus zero error. So for example, before you stand on the weighing machine, you look at it, it says 2 kg. You stand on the weighing machine and you look at it again. It says 80 kg. Are you going to say that you're 80 kg? No, miss. No, 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 no. When I wasn't on the machine, it was 2. I stand on it, it's 80. I am 78. Correct, lor. You just minus the zero error. Okay? It works both ways, even when it's negative. Alright? So we minus the zero error in this case. Okay? So that is the true value. Next. Another way to improve this is recalibrate problem. Recalibrate the instrument. So you need to fix the instrument. You need to look at the instrument, you need to figure out what's going on and figure out if you can fix it. That is the systematic error. So when you shoot something, let's say we go back to the gun analogy or example, if there's a systematic drift up or there's a trend, that means something is wrong lah. Something is wrong. Go and, I don't know, clean the gun and change things out. Okay? That's one type of error that could happen when you take reading. Supposed to get 2.8, or your readings is less than 2.8. Okay, so let's rewind to the back of the phone call with the operator. You call the operator, the manufacturer say, okay, the diameter of the guli or the marble is 2.5 cm. And you look at your readings and you're like, okay, I like that, very close to 2.5 or around 2.5. In fact, if I were to draw the number line, okay, this is 2.5. I get 2.52. 2.52 is here. I get 2.51. 2.51 is here. I get 2.49. 2.49 here and here 2 times. And then I get 2.48. So you can see there's an even scatter or more or less even scatter or random scatter in both directions. Bigger than 2.5 and less than 2.5 because now 2.50 cm is my true value. Okay, so the measured values in this case are both or can be both larger and smaller than the true value and in a random fashion. So a lot like this random scatter, when you point a gun and shoot at someone, of course he's going to die. It's going to shoot, it's going to count as a headshot. But there's also some random stray bullet. So whenever you take a reading in physics, okay, most of the time, you will have some form of random error. It's just that whether it's picked up or not. Okay, so what are the source of this random error? The easiest one to talk about is human. We, me. Yes, we are all sources of random errors because I don't know, maybe there's wrong technique, all sorts of weird things can happen. So I'll just write here, human error. Maybe incorrect or maybe not. Technique can be improved. The not suitable technique. So when it comes to this kind of things, right, techniques in using or set up, using instrument or in the setup of the experiment, most of the time, we will do a lot of this in paper 3. We will identify what is the weaknesses, basically where did the experiment messes up and how do we improve it. It's a very important science skill. What did not work? How can we improve? This is an ongoing process in your brain. That's what makes you human. Number 2, it could be due to natural surrounding errors, surrounding fluctuation, such as temperature, pressure, refraction, maybe got gravity, maybe got friction, so many things, can fill in the blanks. Okay, so we can minimize random error by your favorite technique. Take several readings and average. Because it's random, taking average reading always helps. Like this, if I average up all the dots, the location will be closer to the head. Okay, so take average and find the mean value. All right, so this one will improve. Okay, so in this case, this one improves both precision, meaning you can read to one more decimal point, and accuracy. That's why, because there's human error, human reaction time, all that, you cannot get that, you cannot avoid that. Okay, so the best thing to do is take repeated reading and average. Hopefully all your flaws, your very human flaws, will average out to close to perfect. Okay, all right, so I need to talk to you with another issue, which is the issue regarding parallax error. Miss, is parallax error systematic or random? So most of the time it's random. Random, we blame who? Blame the experimenter, because it's human. So maybe this experiment, whenever he take reading, parallax error is when your eye is not at the right place. You are looking at the thing, but your eye is not on the level of the water, meniscus. You will learn this in chemistry. Basically, your eye needs to be where you want to read. Okay, so the way we get over this, although you don't really use this instrument right now in the lab because you have a digital one, because you're fancy now. Okay, the way it's being improved is nowadays people will provide a mirror. Okay, I'll show you what that looks like. Okay, a mirror at the back. They like to call it the anti-parallax mirror. Okay, so the reading is wrong when your eye level is at an angle, and then you can see the pointer image. The reading is correct when you put your eye right on top of the needle. So your eye has to be right on top of what you want to see. This is random because it could be due to technique. But sometimes maybe you are limited by the fact that you are too short. There's no way to safely, so you're always looking up at the experiment. So then maybe cannot know. Or maybe the experiment is placed at a location where it's hard to see. So if you watch the later vector video, I have parallax error because I was recording using a desk camera that was blocking my eye, my line of sight. Okay, so parallax error depends. So for your paper 3, when you're writing this or when you read questions or MCQ, please consider case by case basis. Don't memorize. Okay, so the only thing that differentiates systematic and random error is this one, is the spread. If the spread is only in one side, systematic. If it's on both sides, random. If the reading is always larger than or smaller than, systematic. If it's both larger than or small, both larger than and smaller than, both and, then that would be your random error. Okay, again, that was lag. Okay, so that's how you differentiate. Everything else, please read the question and interpret it. Okay, speaking of reading a question, let's try a few. MJ20 paper 11. A measurement is taken correctly. Okay, so there's no human error. I'm just going to write here. Human is okay. Legit. Taken correctly. No human error. Okay. but with a ruler at a significantly higher temperature. Ooh, this ruler is in a hot temperature, significantly higher temperature than that at which the ruler was calibrated. The higher temperature causes the ruler to expand. Okay, what is calibration? Calibration is the process where you print this thing on your instrument. I don't care lah, whether it's voltmeter, thermometer, any meter, or the micrometer, anything that you turn, anything that you take a reading, you print out the scale. That is calibration. You decide how to fit the scale in, calibration. Okay. So this one is normal ruler. Okay. Then it says here, the higher temperature causes the ruler to expand. Wow, the ruler become bigger. Okay, I'm gonna expand the ruler a bit, okay? Okay, this one a little bit 夸张, a bit exaggerated, but this one is in hot ruler. So hot, sizzling hot. Okay, so it says here, what describes the effect on the measurement caused by the higher temperature and how the measurement may be improved? Maybe don't overheat your ruler. I don't know. Okay, let's see. Number one, whenever I see long sentences in MCQ, I'm gonna sit like this and I ask myself, time to ready the brain. Okay, that's what Miss Ellie will also say. Time to ready your brain. Okay, so the measurement could be random, or it could be systematic. Which one? Don't know. I highlight first. Okay, and the measurements can be made more accurate or more precise, or more accurate or more precise by taking average. So generally speaking, you are taking average. Okay, so guess what? I can already shoot down some answers. If it's systematic, taking average doesn't help with the accuracy because your reading is always maybe smaller than the real reading. You take average, still smaller than the real reading. So this, nope. Okay. What else? Random. Random can be made more accurate, more precise. So I just now need to decide, is this a random error or is this a systematic error? Okay, let's see. Let's say I measure a pencil. Okay, so I'm going to put maybe I draw a pencil here. Maybe I measure a pencil. Let's say the pencil on the normal ruler is just nice 4 cm. Okay, 4 cm like that. But if I extrapolate down, it is 3.5 cm. In fact, whatever I measure on the hot ruler is going to be shorter than the real reading. I said the reading is 4, I'm going to get 3.5. I take the same pencil, I put back there again, I get 4.1. I'm going to get 3.5 as well. I take the pencil, I put it back again to repeat measurement. Maybe I get 3.8. And then here I'll get 3.2. So it's always smaller than. Okay? Always smaller than because the scale is stretched out. This is a systematic error. So at first, when you think about temperature, you may be thinking, oh, teacher, I know this one must be random because it's external factors. But the question here is, how does the external factor affect your reading? If it affects in such a way where it makes the reading bigger or always smaller, that is systematic. That is the only defining feature. Do not memorize. Analyze. Don't memorize. I'm going to put that on a t-shirt. I'm going to buy my merch. Just joking. I don't know. Am I a teacher? Am I an influencer? Don't know. Okay, last question for the video. All right, this one, you say a student carried out an experiment with an electric current known to decrease with time. Okay, this summer 13 paper 1 2. Okay, so the current will decrease with time. So I expect as time increases or as more time passes, my reading should decrease. Okay, let's look at my reading. From the first to the last, 3.62 milliampere. Okay, decrease to 2.8. Okay, decrease to 1.13. Okay, increase to 1.73. Nani, decrease back to 0.9. Which statement could not explain the anomalous 1.13 milliampere reading? Why? Why you do me dirty? 1.13. You are supposed to fit the trend. Okay, so let's see. The person reversed the third and fourth reading. Could be right. Maybe when you fill in the table, you fill in the wrong cell. Happens to the best of us. Okay, maybe this human error. Possible. He read the ammeter incorrectly. Hiya, this should be 2.13. Hiya, also can, human error. I mean, it also happened to us before. Raise your hand if you did a maths paper, you go like, what the heck? I copy it over and then I get a different thing. Wow, what happened? Okay, don't know what happened. He thought reading at the wrong time. Also can. So all of this is human error. Could it explain things? Yes, human errors is not a mistake one. Which, by the way, human errors has also cost the scientific community a lot of money. A conversion error has sunk a spaceship before. It was a few billion USD. So if you make small mistakes, it's okay as long as you can catch them and try to be a bit more intentional when you're doing experiments. So my elimination is D, but let's look at D. There was a systematic error in the readings from the ammeter. Systematic error will affect every reading, not just one, but all the readings. Okay, so let me show you how this could look like if, let's say, I draw a graph to show you how different the two errors can look like. Okay, so let's say I have a graph of current against time. So they say current decrease with time. So maybe like this. It is my true value. The line is my true value. I do experiment. 3.62, 2.81, 1.13, 1.78, 0.9. So this is the anomalous data. Okay, let me move the 0.9 higher. So the points are balanced. But this one is your anomalous data, correct? So if everyone also anomalous, then the whole graph should shift downwards. So this kind of thing, if there's only one that is problematic, this is normally due to human error. So for example, if let's say I see you in the lab and we do this experiment and then I collect result. And then you come to me and you say, Miss, my answer is not correct. Why? Well, the first thing I do is I'm going to look at your answer and I go and check with your friends. So I'm going to check with your friend Abu, and then I will check with your friend Aladdin, and then I will check with your friend Jasmine. Yes, I'm going through the cast of Aladdin. Okay. Mufasa. Okay, I checked everyone already. But you are the only one with the weird reading. Yeah. So what happened? Human error, your error. Okay. But if everyone's reading is also smaller than the real reading, meaning your entire graph is going to be shifted downwards because all the point will plot down. Now, this one, ladies and gentlemen, is the systematic error. Whereas this one is the random error. Random human error. Okay. All right. Hope that makes sense. I will see you in the next video where we will deep dive into calibration curve and precision and accuracy, because we don't know if any of this is precise. This reading, is it precise? Don't know. I mean, sorry, we don't know whether it's accurate. Is it precise? Precise to 2 decimal points. All right, I'll see you in that one, and we can talk about that later. How do you evaluate the readings that you get in an experiment or a set of data that's given to you? Stay smart. Bye-bye.